A circular cylinder placed in a flow will, under some conditions, vibrate. The frequency of these vibrations, F, is related to the speed of the flow, V, the density of the fluid, ρ, the diameter of the cylinder, d, and the viscosity of the fluid, mu. A cable on a suspension bridge is 2 centimeters in diameter, and the design wind speed is 20 meters per second. Tests on a 1 millimeter wire in a water tunnel gave the following results. And we have a table here of the velocity and the frequency that resulted for those tests. What vibration frequency should be expected for the bridge cable? So this is a model prototype type question. So we'll give our given information here. So the prototype in this question is the cable on the bridge. So for the prototype, we know the diameter of the prototype is 2 centimeters, and we know the velocity of the wind for the prototype is equal to 20 meters per second. And the prototype flow is in air. For the model, where we do our testing, the diameter of the model is 1 millimeter, and the velocity that the model test is done at, there's a whole variety of velocities as given in that table, so we won't repeat those. The fluid for the model testing is water, so the properties, of course, of air and water will come into play. So what we're asked to find is the frequency of vibration for the bridge cable. So the frequency for the prototype is what we're trying to find. So that's what we're after. So our assumptions. This is a dimensional analysis problem, so we'll simply assume dimensional homogeneity. Assume that applies in the analysis. So before we can do the scaling here, before we can equate conditions for the model to the conditions for the prototype, we need to non-dimensionalize this problem. So we have to take a look at the Buckingham-Pi theorem in order to do that. So we begin by saying that the frequency is a function of, so it's going to be a function of the velocity of the fluid, so V. It's going to be a function of density, diameter, and viscosity as well. So density, the wire diameter, and the fluid viscosity. So that's what we're told. So that's the starting point of the Buckingham-Pi theorem. Next thing we need to do is identify the dimensions of each of these. So frequency will have dimensions of 1 over time. Velocity, length per unit time. Density, mass divided by L cubed. Diameter just has dimensions of length. And the dynamic viscosity is m divided by Lt. So those are our fundamental dimensions. So we notice we have 1, 2, 3, 4, 5 parameters here. And we have 1, 2, 3 unique dimensions: time, length, and mass. So j is equal to 3. So we should expect n minus j, or 2 dimensionless groups. So the next thing we do is select our repeating variables. Now we don't want to select the frequency for the repeating variable because we only want that to appear in one of the dimensionless groups. So we'll pick velocity, density, and diameter. So notice this group, if we choose those 3 variables, there's no way that we can form a dimensionless group with just those 3, because density is the only one that contains mass. So there's no possible combination of those where the mass would cancel out. So that's a valid choice for repeating variables. So we're going to let our repeating variables be V, ρ, and d. So our first pi group then, pi 1, will have V to the power a, ρ to the power b, and d to the power c, and then we'll begin by non-dimensionalizing the frequency. And that has to be a dimensionless number. So substitute in for each of these variables their respective dimensions. So v is L over t, that'll be to the a, m over L cubed to the b, just L to the c, and then frequency is 1 over time. So that has to be m to the 0, L to the 0, t to the 0. So we can form one equation with each of our three dimensions. So length, we get a minus 3b plus c has to equal 0. Mass, we get, there's no mass in this term, we get a b from that. No mass here or here. So we get directly from that b is equal to 0. Time, we get negative a for this one. Nothing there, nothing there. Minus 1 is equal to 0. So a is equal to negative 1. So now we take a of negative 1 and a b of 0 and go back to this one, and we get negative 1 plus c equals 0. So we get that c is equal to 1. So there's our three values, a, b, and c. So now we can form pi group 1 from those. So we're essentially just rewriting this with the value of a, b, and c that we found. So we have our frequency first. A is equal to negative 1, so the v goes in the denominator. Rho, b is equal to 0, so there is no rho in the result. And the power of d is c, and that's positive 1, so that goes in the numerator, like that. And if you take a look at the units or the dimensions of each of those, that's a dimensionless group. So the dimensionless frequency is f times d over v. And that's known as a Struhel number. So that actually has a name. So our second pi group, we get the same way as the first one, starting off at least. So v to the a, rho to the b, d to the c. So notice so far that's exactly the same as this. So it's our repeating variables. Only now we take the only remaining variable here, our viscosity, and put it there. And that has to form a dimensionless group as well. And we can sort of see where this is going. This is going to come out to a Reynolds number, but we'll go through the details of how that works out. So substitute in the dimensions. So velocity, length over time to the a, m over L cubed to the b, and L to the c, and then viscosity is m over LT. So that's m to the 0, L to the 0, t to the 0. So the L gives us an a minus 3b plus c minus 1 because of this. M, again, nothing there. Get a b plus 1 is equal to 0. So that lets us say that b is equal to negative 1. And then t minus a minus 1 equals 0. So that tells us that a is equal to negative 1. Take a and b back into this one. We get negative 1 plus 3 plus c minus 1 equals 0. So that tells us that c is also negative 1. So a, b, and c are all negative 1. So we can write down our second pi group then, and we get mu in the numerator, and all three of these are in the denominator because negative 1, negative 1, negative 1. So rho v d. And you probably recognize that as the inverse of the Reynolds number. So we can invert that just to make it a more conventional dimensionless group. Remember, we can take a dimensionless group and raise it to any power we want, and it's still a valid dimensionless group. So I just raise that to the power -1, so it becomes a Reynolds number. So we found both dimensionless groups. That allows us to rewrite our function in dimensionless form. So frequency times d over v is a function of a single parameter, rho vd over mu. So that's what dimensional analysis tells us, that dimensionless frequency is a function of this. So now what we need to do is do a bit of investigating as to what that function is so that we can do the scaling. So if we take a look at our data back here, we notice that for tests done in water, we have a whole series here of velocities and the vibration frequency that resulted. So what we're going to do is calculate, for each of those, we're going to calculate the Reynolds number and the dimensionless frequency. Okay, so we'll just make a little table here. So the velocity in meters per second, the frequency in hertz. So those two, we'll just be repeating the data that we were given above. But we want to get the pi 1 group. So that's our dimensionless frequency. That will be this, and that's dimensionless. And our pi 2 group, and that's our Reynolds number. So we can calculate all this, and then we'll take a look at this and see if we can see the relationship between them. So I'm going to fill this table in. 3 meters per second gave 605 frequency in hertz. Calculate this pi 1 group from that. Now remember, all of this model testing we're talking about here, the density would be 998 kilogram per meter cubed, and the viscosity would be 0.001 Pascal seconds, because we're doing this in water. So that's the density and viscosity used to calculate this. Second test, 5 meters per second, 993 hertz. Calculate the Struhel number, 0.199, so almost the same as that. And the Reynolds number is larger because the velocity is larger. Double the velocity, we go to 1990 for a frequency, 0.199 again, and 9980. So we'll just fill in the rest of this table and we'll take a look at it. So that's the entire table filled in. Now the most interesting thing here is if you look at this pi 1 group, it's essentially constant. So over quite a wide range of Reynolds numbers, this Struhel number is constant. So that's the conclusion we can reach by analyzing this data and looking at it. So that means that the Struhel number appears to be independent of Reynolds number. So in fact, this functional relationship is just Struhel number equals a constant, and the value of that constant is essentially 0.2. So we can take that knowledge that the Struhel is constant now, and we can go to our prototype situation, which is the bridge cable. So for the bridge cable, so pi of the prototype is equal to 0.2, so that's going to be equal to the frequency we're looking for, multiplied by the diameter of the bridge cable, that's 0.02 meters, divided by, put meters in there, and in the denominator we have 20 meters per second. So the frequency that results from this, do this calculation, we get a frequency of 200 hertz. So we've calculated the frequency that the bridge cable will vibrate at. Now, you may have noticed that we calculated that frequency based completely on our first pi group by setting this pi group equal to 0.2, because we looked at this data and we saw that this really didn't change. It was 0.2 for all of the Reynolds numbers in the water tunnel experiments. Now what we can conclude from that is that over this range of Reynolds numbers, this pi group, the Struhl number is constant. So really, before we can accept this as an answer, we really should check and make sure that the Reynolds number in the scaled up or in the prototype situation is within this range. If it's within this range, then we're justified in concluding that the Struhl number, or the pi 1 group, will be 0.2. So that's what we need to do next. So we need to calculate the Reynolds number for the prototype. So remember, our Reynolds number, which is our second pi group here, is equal to the density times velocity times the diameter of the cable divided by the viscosity. So for the prototype situation, the fluid is air. So the density is 1.2 kilograms per cubic meter. This is just at standard atmospheric conditions. The velocity is 20 meters per second for the prototype. And the diameter is 2 centimeters, so that's 0.02 meters. And the dynamic viscosity of air at 20 degrees C is 1.8 times 10 to the minus 5 Pascal seconds. And you can get that viscosity and this density from table A3 in your textbook. So when we calculate this out, it comes out to 26,667. So you take a look at that Reynolds number, you'll notice that it's within this range. It's actually between those two. So it's within the range, so we can conclude that the Struhl number is 0.2, and therefore this frequency that we calculated in the prototype situation is correct. So we can finish off by making a statement that the bridge cable will vibrate at 200 Hertz.